The sound you hear from a piano results from a vibrating string. Those vibrations go through the bridge to the soundboard. Soundboard imparts its vibrations to the air, and the air has acoustic waves that go to your ear and you hear a sound. Now the pitch of that sound is due to the string, the characteristics of the string, the characteristics of the metal itself, its bendy properties, the length of the string, its diameter, and its tension, how tight it's pulled by the tuning pin. Now, what you hear isn't just the basic pitch. What you perceive as the pitch is actually a combination of many vibrations, or many modes of vibration. A vibrating string is called a harmonic vibrator because it vibrates in these many modes, and these modes are integral multiples of the fundamental. In physics, the mathematical solutions to the frequency of the string are actually n times that function of the characteristics, length, diameter, and the tension. For example, a string with a fundamental frequency of 110 cycles per second also vibrates at frequencies of 220, 330, 440, 550, and so forth. In this example, you're going to hear a combination of those pure tones. The basic pitch you perceive is always the fundamental. These multiples are called harmonics or partials or overtones. Those three terms have slightly different meanings, but it's basically the same idea. Now, all musical instruments that produce pitches are essentially harmonic vibrators, whether the vibrator is out of a string or some kind of bell or a column of air. Wind instruments are all basically a column of air. The differences in timbre or the quality of sound happen because of different relative intensity of the harmonics. For instance, a flute has a strong fundamental compared to the upper harmonics. Violin has stronger upper harmonics. Musical instruments that have no or little discernible pitch, such as drums, can be called inharmonic vibrators because their partials are not necessarily harmonic. Now, if we look at those integer multiples as a scale on a keyboard, you see that the first 6 partials correspond to the notes in a major triad. So a major triad and all the notes in a major scale, for that matter, are harmonically related. So in other words, the frequency of those notes are related by simple mathematical relationships. So that's why these notes have a kind of a consonant sound. Now in music theory, we've all been taught this circle of fifths, where we have C at the top and we kind of progress around all the various key signatures, C, G, D, A, and so on and so forth, till you get back to C. Now, as we saw, each fifth is related mathematically. So you take the example of A 110, say, multiply that by 3, divide it by 2. Anytime you divide or multiply by 2, it's just an octave. So you can create this circle of fifth by multiplying by 3 halves all the way around. Great. So here's another thing we can do. Take that starting note of C, 32.6 cycles per second, and then say we keep multiplying that by 2. Now we have a conundrum. It's a little bit upsetting because if you go from C to C around the circle of fifths, you get a number. If you go from C to C just multiplying by octaves, you get a different number. It's very unsatisfying. And that little conundrum is called the Pythagorean comma because Pythagoras was the first guy to describe it. Of course, if you think about it mathematically, why would you expect these numbers to be the same? Because on one hand, you're multiplying by 2's, and in the other case, you're multiplying by 3's. They're not going to line up. But if you're trying to tune a keyboard instrument, you're faced with this unhappy situation that you can't really tune perfect octaves and perfect fifths at the same time. Now hold that thought. Now going back to what we learned in basic music theory, here's what most of us were taught. Major scale consists of these little egg-shaped notes that go up on a staff like this. And a major scale consists of whole steps, except for a half step between the third note and the fourth note, and a half step between the seventh note and an eighth note. Now, in this view of the world, The A major triad is made up of the frequencies which are built in this system, which are whole steps and half steps, each half step being equal. That's called equal temperament. Each half step is exactly the same distance from one note to the next. If you look at those frequencies, for instance, that A major triad again, A220, C sharp would be 277.2, E would be 329.6. But if we go back to those harmonic ways of looking at things, the C sharp is 275.0, the E is 330. Here's another conundrum. Of course, the fifth is not correct, as we learned from looking at that circle of fifths thing. And the third is even more incorrect than the fifth. In fact, it's off by 14 cents, where one half step is 100 cents. So that third, harmonically compared to equal temperament, is off by 14 cents. Here's an example. See if you can hear this. It turns out, if you want to, you could tune a keyboard instrument so that the fifths and the thirds in the keys of, say, C major, D major, and E major are all harmonically perfect. But guess what happens to all the other keys? Here are some examples. Here are some major triads with the notes tuned harmonically correct. Here's D major. Here's F major. Here's G major. But if you tune an instrument so that, say, the white note keys are tuned in a harmonically good way, guess what happens to the black note keys? They get all goofed up. Here is D flat major. Here's G sharp major. As you probably have already realized, this is all leading up to a discussion of temperament. Temperament refers to how musical instrument tuners solve these dilemmas. Equal temperament is a compromise where every key is equally non-harmonic, but only slightly non-harmonic. In this chart, the green bars represent that 14 cents, and the blue bars represent that 2 cents that each major third and each fifth are incorrect compared to doing things harmonically. In a temperament that's called quarter comma mean tone, that unequalness is split between 4 keys. So the major thirds in the white note keys have almost no incorrectness harmonically, but some of those black note keys are really out of whack. It's kind of like a game of whack-a-mole. You're never going to get rid of any of this harmonic incorrectness. All you can do is find some compromise. And there are many different temperaments. For instance, there's one called Velati temperament where that incorrectness is kind of spread out among the keys in different ways, and you have key color. There are a lot of people who are interested in temperaments. There are different ones that were popular in different places and at different times. This is a whole another discussion. But for the purposes of piano tuning, we're going to stick with equal temperament.